Okay, welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about, science and math. And today we are in AP Chemistry doing part 2 of the Unit 3 notes. So if you didn't see part 1, go back and watch it. I've already had a lot of views on it from posting it this morning. Okay, so what we've been talking about is the electromagnetic spectrum. And this is an example question. It says, what type of spectroscopy would be responsible for the change from 1s2, 2s2, 2p5 to 1s2, 2s2, 2p4, 3s1. So an electron has gotten excited. It's not in the ground state anymore. It went up. Which one of these can promote an electron? Can radio waves do it? Can microwaves do it?
I thought microwaves.
What?
No, they rotate. Microwaves rotate.
Right. So you have to memorize this. It would be UV light. UV would be able to promote it. Now, visible actually can too, a little bit. I don't know about this one, about this particular element, but when you have glow in the dark, that's visible light can cause the electrons to jump up and then jump back down for the glow in the dark. So light can do it, but definitely UV, light with more energy, could do that. What type of spectroscopy will be responsible for bending OH bonds in water? So this one is the one where these molecules are vibrating. So what can make them vibrate? It's our IR, right? Our infrared, the heat. The heat can. Okay. All right, let's go on to properties of photons. Now, I missed teaching something, and it was in the I do, we do's that should have been here. Let's see if no, it's not here. Okay, I'm going to go ahead and teach it to you now. I taught it to the other class when we looked at I do, we do's. But I want to talk about it now so it's on the video, so if anybody's out, they'll hear it, because they won't hear me talk about the I do, we do's. Okay, so photons are little packages of light. They have a dual nature. Does anybody remember what the dual nature of light is? What it can behave like? A what? It can be a wave and a particle, right? So it can be a wave flying through a vacuum. It's got a wavelength. We've proven all of that. But there's also something, and it's on my poster over there. There's your anchor chart. It's called the photoelectric effect. And what it is that electrons have this, photons have this dual nature where you can take light and shine it on metal and electrons will splash off. So it shows that it's like it's a particle that can make something splash, that can make something move. So it's that dual nature. And if I'm saying this right, y'all can fact check me. It was Niels Bohr, the guy with the Bohr model, who thought of this. And Einstein said, that's stupid. That is not right. And Bohr was right and Einstein was wrong. So, sometimes people think he's like a superhero who can't ever be wrong, but he was wrong about the photoelectric effect. But y'all can fact check me and make sure I got the right scientist. I'm pretty sure I do that. So that's the photoelectric effect. You see it with like this kind of calculator where it's got this little shiny metal thing here. That's what's going on here. Light is hitting that and it's causing electrons to move. The movement of electrons generates electricity and it will run your calculator. It's based on that principle. Okay, so there's a question about that in your I do, we do, but it's not addressed here. Okay, when a photon is absorbed or emitted by an atom or a molecule, the energy of the species is increased or decreased by an amount equal to the energy of the photon. The wavelength of the electromagnetic wave is related to its frequency and the speed of light by the equation c, the speed of light, equals wavelength times velocity. The energy times frequency. See, this always confuses me because that is velocity, and it used to be that you would see frequency as like a little cursive F, and now they've changed it to that. And when it's frequency, now they usually draw it more curved on one side, but like that's not very curved. Anyway, that's frequency. The energy of a photon is related to the frequency of the electromagnetic wave through Planck's equation, and that's it. And h is Planck's constant. Okay, so let's identify these formulas here. C is the speed of light. Now, in physics, we always use 3, but the lady who did these notes is using 2.998 times 10 to the 8th meters per second. I need to look and see if y'all have to use that on the AP test or 3, but like all through college physics, we use 3 times 10 to the 8th. So I don't know about that. Okay, the little upside down Y is the wavelength. Okay, that's measured in meters. That one's in meters per second. The frequency is in hertz, or 1/2, or second to the -1. And those are all the same exact thing mathematically. There's just different ways of writing the same thing. Y'all know that a negative exponent means it goes down to the denominator, right? So that's the same thing as this, and they just made a name for this and called it hertz. But it's second, inverse second. Okay, so this formula, big E is energy, always. And the unit of energy is joules, okay? H is Planck's constant, and I think it is given to you on the test. You wouldn't have to. CST means constant. I think that's got a C in it. Y'all can check, y'all can fact check me on that too. But anyway, it's 6.626 times 10 to the -34. And the unit of it is joule seconds. Joule dot seconds. Okay. Oh, and that is frequency, which we already talked about. Draw a little arrow up there. Okay, so here are some little equations. And then the other thing you have to use a lot is 1 times 10 to the -9th meter is a nanometer. I'll give y'all a second to write that down, and then we'll look at some typical problems. There's a very typical problem in the I do, we do's also. Excuse me. I talked too much today.
What's that say, hertz or what?
Hertz, or 1/2, or second to the -1 power. Those are all the same thing.
And is that 10 to the -34?
-34, yes, joule seconds. Okay, y'all ready for the math? Not yet. I'll scroll just a little bit now. I think this is like kind of an easy part of AP, because they give you the formulas. You just have to plug the numbers in where they go. Like there are harder problems that y'all will do. These are not them. So these aren't too bad. Calculate the wavelength of light. So I like to annotate. So wavelength is what I don't know, question mark. That has a frequency, put that little V on there, so it's this number right there, of 1.5 times 10 to the 15th hertz. Okay, so we're gonna start off with our speed of light is equal to wavelength times frequency. So the speed of light, I'm going to use 3 because I'm lazy and I think the other number is unnecessary. But if we have to use the other one, we will. 3 times 10 to the 8th meters per second equals the wavelength, that's our unknown, so I'm leaving it as a lambda. That's the Greek letter lambda, times 1.50 times 10 to the 15th hertz. So I divide 3 times 10 to the 8th, divide by 1.5 times 10 to the 15th, and the answer for the wavelength is 2.00, going by sig figs, times 10 to the -7th meters. Put a box around it, get in the habit of marking your final answer. You're more likely to get a good score on the AP test and all your little science and math tests. Okay, how do we feel about that? Okay, can I scroll down?
I can't see because of the phone. Wait a second.
Hold on, let's see.
Wait, is all that on the little cheat sheet for the AP?
Let's look at it and see. I'm gonna give it to you and let you look. I think all those formulas are though. And I think the speed of light, if it's not on there, they're all together here somewhere. Here, oh, you already got one?
Yeah, I got one.
Yep, look at that. Look and see, I think they're all on here. Maybe I'll let
Yeah,
you-
speed of light is on here.
And what does it have, 3 or 2.99?
2.998.
Ah, that is just silly. Yep, there it is, speed of light, 2.998 times 10 to the 8th. You're gonna have to use that. There's Planck's constant, charge of electron. Oh, and there's our E. Then see, they even tell you what these symbols mean.
Yeah.
And they have the formulas right there. There are the formulas right at my finger. Okay. All right, calculate the energy of light that has a wavelength of 450 nanometers. So those are our two formulas. We're gonna start by getting the frequency. So we're going to start with C equals wavelength times frequency. So I'm going to say 3. I'm going to be rebellious and say 3 times 10 to the 8th. If it's good enough for physics, it should be good enough for us too. Times 450 nanometers. We need to change those to meters, so we're going to use that, and it's 4.5 times 10 to the -7th meters V. So we divide both sides by that, and we get the frequency equals 6.7 times 10 to the 14th. Oh, that's a really bad looking 14. It's way too big. Hello. Now, were you here yesterday? Did you get the notes? Okay. We're finishing the notes. Okay. 14. Look, that's a more acceptable size of a 14. Okay, so now we want the energy. And energy equals Planck's constant times the frequency. So Planck's constant is equal to 6.6, lift out the 6, 26 times 10 to the -34th. And we're going to multiply that times our frequency over here, 6.7 times 10 to the 14th. And the answer is, we're going to write it up here, 4.4 times 10 to the -19th joules. Put a little box around it. Make it look like it goes down here. Ta-da! So y'all agree this isn't the worst part of AP Chem? Most of y'all are pretty good in math, and y'all can do a 2-part. The 3 things is not a hard equation. The only thing that makes it hard is you have to use one co-equation and get an answer and then plug it into the next equation. That's the only thing hard about it. Okay, I'll give y'all a second to write that down. I'm gonna go get some eye drops while y'all do that. Okay, the next part is pretty easy. Okay, for the next one, they give us one of those little graphs where we figure out the orbitals. So looking at this, do you think we're starting from this side or that side? We're starting from this side, right? Because we can see there's our what? What is this one? 1s2, right? So what's that one? 2s2. What's this one? 2p6. What's that one? 3s2. So what's that one? 3p. How many do you think it is? 3. Because see, if that's 2, that's a third bigger, that's 3. With that in mind, which element is it? Phosphorus. Yay, y'all are so smart. That makes me so proud that y'all can do that. That's 100% an AP question you just answered. That you don't learn that. Phosphorus. Okay, calculate the wavelength needed to remove a valence electron. So those are our valence electrons, right? This is our energy right there. So we're going to start with that energy, 18.24 EVs. These are EVs. But we're going to need to change that to joules to be able to calculate it. So the first thing we're going to do is we're going to use our conversion factor right here. 1 equals 1.6 times 10 to the negative 19 joule. Okay. And we get 2.9 times 10 to the negative 18th joule. Okay. And now we're going to use our equation. Wavelength equals Planck's constant times the speed of light divided by energy. So they're putting those two equations a little bit to get that. So Planck's constant is our 6.626 times 10 to the negative 34. I'm going to leave off units, but on the real AP test you should include them. Times our speed of light, 3 times 10 to the 8th, that's me being rebellious, divided by our energy that we just got right here, 2.9 times 10 to the negative 18th, and we get the wavelength is 6.8 times 10 to the negative 8th, and that is meters. Make sure you can see that decimal point right there. That's our wavelength. Put it in a box. Okay, that was a little more complicated because they kind of put the equations together, but you can always do it in steps. Okay, y'all ready to go on? Last section. Woo! 13 sections, it's so big, but this one at least is fun and easy. Okay, Beer-Lambert's law. So this is this thing, and we give you the big picture first. You can use a machine that looks like this. We had one that looks like this, and I threw it away. I'll tell you why in a minute. But anyway, you can use a machine like this. You can put a solution in this little square test tube called a cuvette, and you pop it in the machine. You open that little black top and pop it in there, and it can tell you the concentration of the solution in there. Isn't that cool? For it to work, it has to be a colored solution. Clear doesn't work, but if it's colored, you can get a concentration. Okay, now why I threw it away. So we had one of these, and it was used by us in AP Chem and in physics for this lab. That's why we had it. But when COVID hit, they just left, and they left chemicals out. There were open chemicals in the stockroom. There were open chemicals in the sink. There were open chemicals on the countertop. So I got hired summer of 2020 to come here, And I was not the teacher. It was a different AP chemistry teacher here at that time, and came in here, and those chemicals had been all spring when y'all left and went home, all summer in the heat, all that Georgia heat, got here in the fall, and there was a white haze in the room, just floating white chemicals, where those chemicals had been just happily little reacting chemicals all the way back to the stockroom. This thing was in the stockroom, and I got it out, and not only was it, but all this other stuff was covered in white powder. And when you touched the white powder, it burned. And when I saw it, I was like, I am so glad I am not the AP Chem teacher here. I am so glad I don't have to clean up this mess. I had to clean up the mess. Of course I did. It was overwhelming. Like, it was terrible. So my son, you know, he's a student getting a PhD in chemistry at Georgia Tech. And he's like, I'll help you. So he came and he helped me. And we had on gloves and we started just going through everything. And whatever chemical it was, and I don't know what it was burning through gloves. As we took every chemical, we would take it and wipe it down with chemicals to neutralize everything and put it back on the shelf. We're wiping off the shelves, we're wiping off everything and getting rid of all of this chemical. And as you're doing it, the gloves are starting to turn brown as they're burning, and then the holes are getting burned in. So we had on layers and layers of gloves. I would have quit. I would have just started crying, but Nathan was like, come on, we can do it. We can do it. We spent hours and hours and hours. Like, I know one day we spent 8 hours just trying to clean it up. It was so overwhelming. So I got this machine out of the stockroom, plugged it in, and like everything was pretty clean. I plugged it in, and a puff of that white smoke came out. And I'm like, nope, and I threw it away. So Miss Raymond, the physics teacher, saw it, and she's like, you threw away our machine? And I told her what happened. I'm like, if you want to get it apart, take it all apart, clean all the interior components, and put it back together again. You are welcome to, but I am not cleaning that thing. And she said, leave it in the trash. So it got thrown away. I looked on eBay, and you can buy them for about $300. So, but anyway, we have a different machine. So ours are these little boxes that I found in the stockroom. Also, that's when I threw away the centrifuge too. That thing also was full of the burning white powder. We don't know what it is. It's just called the burning white powder. So that went in the trash too. But anyway, I found these other little boxes. They were not full of burning white powder. They were in that stockroom, not that one. And they were in plastic and in a box, so they're safe. And we're going to use them instead. So don't worry, you're going to get to do this lab, just not with that machine. Okay, so we can measure the concentration of colored substances by seeing how much light passes through it or how much light is stopped by the solution. The measure of light that is stopped or absorbed by a solution is referred to as the absorbance. Okay, so a spectrophotometer or a colorimeter can be used to measure the absorbance, okay? The more the concentrated the solution is, the less light that can pass through, and the greater the absorbance. The light is being absorbed, it's not passing through, so it has a higher concentration. Does that make sense to you? You can follow that? So here's a little picture of your light source, and then it shines it through your sample, and it sees how much it absorbs. Okay, next idea with this. So this is fun. This lab's a little bit hard. So I was gonna have us do it tomorrow. We were gonna figure out the concentration of blue Gatorade. That was gonna be our job. But last year they struggled with it a little bit. So we're gonna do, we also have this as a PhET lab. So we're gonna do the PhET lab first, let you practice it virtually, and then do it with real. So I think it'll go smoother and be faster that way. All right, so first of all, you put your little sample in, your unknown, and it gives you this little graph. Ours are gonna be attached to our computers. You'll need your laptop on this day. And then you look at the graph and you see where it's the tallest. Wherever it's the tallest, that's the best wavelength. So it's whatever is closest to 1 is what I think she wants here. See how that's 1? Whichever one's the tallest, closest to 1 is the best. So looking at this, what number do you think is the best? 525, right? 525 nanometers. Okay. All right, so that's step 1. Then you prepare solutions where you know the concentration. And you put them in the machine one after another, and it makes a graph of them. And it'll make a straight line. Then you take your unknown, and it's going to tell you an absorbance. You're going to put it in the machine. And then you can go over to the line and down, and it will tell you the concentration. Now, ours, I think, does it automatically. It does this. But if you were doing this old-timey way, where you have to plot it, then you would also, you're going to be you would use this formula, and you would be getting the slope, okay? But I think ours, so another thing about ours, with that old one, the older one back there, you have to put in a blank. You have to put in something that is black, that absorbs all the light, and it like comes with your machine. And so ours didn't have one. So I took one of the little cuvettes and I filled it with black paint from my arts and crafts area over there. And that worked pretty good. And I thought, we don't have to have paint, it's too messy. And I put a piece of black construction paper in one, and that worked pretty good. And then I watched more videos on how to use our machines we have. And you don't have to do it, it automatically does it. And that's why you didn't have to, why it didn't come with a black one. Anyway. That will all make more sense once y'all start doing it. Okay, so you have to create a calibration graph with your known concentrations and their corresponding absorbance values. This graph is linear, and the slope of the line will give you the molar absorptivity constant. The greater the concentration of the solution, the more light that is absorbed, the greater it is. Okay, so this is the little square test tube. It's called a cuvette, and they're always 1 centimeter on each side. The reason why is because the length of this test tube is this, and anything multiplied by 1 is itself, so it makes the math easier. It takes away a variable by making that one 1. That was very smart of whoever thought to do that. So big A is the absorbance. Okay. E is the molar absorptivity constant, and it is found from the slope of our graph. B is the path length, and that is 1 centimeter. It's 1. So it makes the math not important. And C is what you're usually looking for, is the concentration. That's sort of the point of all this, is to be able to get the concentration. And concentration, remember, is square brackets, and it is molarity. The unit is big M. And it's kind of fun because we're going to do it with Gatorade, and that's kind of fun. All right, can we scroll? Everybody good on that? And it's always fun when you have Greek letters. Makes you feel smart. You're doing things with Greek letters. Okay, so on the AP test, they're going to ask you about this. And they're going to tell you situations, usually. This is how this one usually goes. And then they want you to know what went wrong. So like they'll say, you get a concentration, and it's too low. It should have been higher. What could have gone wrong? And so it says here, flushing the cuvettes with water. So some water remains in the cuvette sticking to the side, which slightly dilutes the next solution. This could be avoided by using new solution to flush out the previous solution. So that's what they're going to want you to say is, oh, what did the person do wrong? Well, they probably rinsed out their cuvette with distilled water, and there was a little bit of water still in it. So therefore it made it less than what it should have been. So here's another one. You can also have failure to calibrate using a cuvette filled with the same solvent mixture, usually water. The result subsequent, so first you put in the black one. Then you put in one that's full of just distilled water. Then you put in ones that you know the concentration. Then you put in the one you're looking for. That's how you do it. Okay, so results. Subsequent measurements may include some absorption due to cuvette and or solvent, which will lead to a higher concentration being calculated. So what you do instead is you use a blank. A blank cuvette, that one is going to just have the distilled water in it. Okay, here's another one. Failure to wipe off. So this equipment is so sensitive that if you don't wipe your fingerprints off of the cuvette, it will read them and say that that's part of the concentration. So you get a Chem wipe. So I've got some back there still. I was thinking, oh no, I didn't buy any new. You get a Chem wipe. It's a special little tissue, and you wipe each side before you put it in. It's got it where it's like frosted on two sides, and it's okay to hold it on the frosted sides. But if you hold it on the side that the light's going through, then your fingerprints are gonna mess it up. So you wipe it off, and then you hold it on the frosty side and put it in the machine. All right, and so what you should have done was use a Chemtech wipe. So cool that she got a little picture of it on her notes. Okay, so it says if the absorbance of an unknown sample is 0.275 at 420 nanometers, what is the concentration of X in the unknown sample? So one thing you could do is kind of get an idea of the answer. That's at 275, so I could go about right here, go over and down, and I can see that it's going to be right in there. Do you see that? Then it looks like it's going to be around 0.005 something. Just eyeballing it. And it looks like it's a little more than 0.005. Just eyeballing it. You see that? Now your computer, I think, well, usually you type in what it is and it will tell you the answer. But if not, and you have to do this math, here's the math. The slope, as you know, is rise over run. Y'all know what I mean? It's y over x. So it is equal to, we take a known point to get the slope. So we're going to use 0.1 divided by 0.002. And if you divide those out, it's 50. Our slope is 50. Okay, so that's our E. Our formula, I always think it kind of looks like ABC, but it's a EBC. Okay. Now, if we solve this for C, it's A over EB. So we're going to write that. C is what we're looking for. The absorbance, we know it was given to us. 0.275 divided by 50 times 1. And we get 5.5. See, didn't I do good? Just sort of eyeballing it. Times 10 to the negative third is our molarity. We can put it in square brackets. Y'all like that math? I like this math. It's not too hard. And it looks fancy. It's got a Greek letter in it. It looks fancy. I think y'all will like using the machines too. You feel high tech when you're in lab needing a computer, right? You feel like Dexter in Dexter's lab or something. You got your computer, you're doing a little experiment. Okay. And the computer is actually helping do the experiment, not just putting in data. Okay, here's another one. A 1.41 molar solution of unknown X is analyzed via UV spectroscope. The sample is dissolved in ethanol in a 1 centimeter cuvette, because they all are, and the molar absorptivity is 0.728. What is the absorbance for this sample? I'm going to see if I can scroll up somewhere. Can I scroll? Not much. Okay. So absorbance equals EBC. So I know that the absorptivity, that one is the E, is 0.728. B is 1, and C is the speed of light in a vacuum. C, 1.41. Oh, but we have this. Our molarity, that's our concentration, not C, wrong one. 1.41 molar. Okay, we multiply it all out, and you get 1.03 is our absorptivity, and it has no units. It's just a number. All the units cancel out. Okay, how do we feel about that? Not bad? All right. Get out something. Science is great.